Alright, welcome to online lecture 8.3. Today we're going to be talking about two things, moment of inertia and Newton's second law for rotation. So moment of inertia, inertia is how hard it is to start and stop something moving, and moment of inertia for rotating objects is just that. It's how hard it is to start and stop something rotating. How hard it is to stop something rotating. And you can actually figure out they quantize this. Like, we've done a couple of examples. If you remember in class, we've probably done where I had my two batons, and one of the batons had the steel weights at the end, and the other had the steel weights in the center. And this one was hard, and this one was easy. The other thing that we did, if you remember those two, like, horse race that we maybe did, where I had a solid ring and just an outer edge. This one was the hard one, this one was easy, and they're exactly the same. They are related to where the weight's located. So moment of inertia it's about where the weight's located as much as how much there is. That if you have more weight farther away from the center, you'll have more inertia. And it's the same with if you have more, you'll have more moment of inertia. If you look on page 206, there's a chart that talks about all the different moments of inertia. So if you had a hoop, or if you had a solid cylinder, or if you had a sphere of radius r, if you were rotating a rod around the center with length L, or a rod around the end, or if you had a square block, these are all the different ways to find the moments of inertia of each of them. And you'll notice that this one's the biggest. It has more weight, assuming they all have radius r. The biggest one is the hoop, because it's 1 mr squared. This one's 1/2 mr squared. This is 2/5, so 0.5, 0.4. And notice that there's more and more weight located towards the center, which makes it easier and easier to start and stop moving. So the table on page 206. Is a good reference when you need to talk about the moment of inertia. The next thing I want to talk about is Newton's second law. Newton's second law for rotation. Well, Newton's second law in general is F equals ma, but that's for linear movement. For rotational movement, instead of F, we have a torque. Instead of mass, we have the moment of inertia. Because not only does it depend on how heavy it is, but it also depends on where the movement where the mass is. And then instead of acceleration, we have angular acceleration. So if you want to speed up or slow down something spinning, you have to go through Newton's second law. Just like if you wanted to speed up something or slow it down, you have to apply a force to it. If you want to speed up or slow down something rotating, you have to apply a torque to it. So torque equals moment of inertia times angular acceleration. Now what I'm going to do, I'm going to go through example problem number 4 on page 209. So example problem 4 on page 209. It says you have a solid steel wheel. So I've got a solid steel wheel here. And it's got a mass of 15 kilograms. And a diameter, mind you, got to watch out, of 0.44. So I know that it's got a radius of 0.22 meters. It starts at rest and you want to make it rotate. So the initial angular speed is 0 and you want to start, the final speed is 8.0 RPM. And the time you want it to take is 15 seconds. Okay, now in order to do this, what we're going to do, and it wants to know what torque. So torque is the question mark here. So what we're going to do is utilize Newton's second law here. So because we're looking for torque, and we're going to take the moment of inertia times the angular acceleration. Now I'm going to, instead of just finding the angular acceleration, I know that the angular acceleration is the change in velocity over the change in time. That's the definition of acceleration. Remember that acceleration is just change in velocity over change in time, and angular acceleration is change in angular velocity in time. So that's, I'm just substituting this in. Because the moment of inertia, I'm going to turn back to page 206, and I have a solid cylinder. The moment of inertia is 1/2 mr squared. That's from page 206. And then my delta omega over change in time. So now I just substitute everything in. The mass was 15 kilograms. The radius was 0.22 squared. My change in angular velocity, I need to make sure that this is in radians per second. So I can't just go plugging this in to right here, because I need to change 8 rotations per minute into radians per second. So 1 minute is 60 seconds, and then 1 rotation is 2 pi radians. So I'm going to take 8 times 2 pi divided by 60, and I get 0.838 radians per second. So this is the number. So I'm going from 0 to 0.838 radians per second. So I'm going to put 0.838 radians per second, and the time is 15 seconds. So now I just ram this whole thing through on my calculator, and I can figure out how much torque it takes to start cranking this solid steel wheel from rest up to spin it up to 8 RPM in 15 seconds. So now it's just a bunch of plugging everything into my calculator. So I'll take 0.5 times 15 times 0.22 squared times 0.838, and I'll divide by 15, and I get 0.02 that's going to be Newton meters. Let me see real quick. 8. I think that I might have gotten my radians per second wrong. 8 times 2 pi divided by 60. No. Oh shoot, this was revolutions per second. So yeah, I was wrong. So this is wrong over here. Okay, I made a mistake. This, at the very beginning, the problem says 8 revolutions per second. So to change this into radians per second, all I got to do is take 8 times 2 pi. And that will give me radians per second. So that's 50.3 radians per second. So this is 50.3. And that's the number that goes in here, 50.3. Because I was looking at the answer in the book, and I didn't do it quite right. Something was screwy. So now I think that if I redo this, 0.5 times 15 times 0.22 squared times 50.3 divided by 15, and I get 1.21. And that's better. So that's 1.2 Newton meters. Yep, and that's correct. That's part A. So part A says, what's the torque? Part B says, what if you wrapped a string around the outside of this and you were to pull on the string and this was wrapped around the outside? How much force should you pull on the string with to exert that torque? So, well, torque is just force perpendicular times distance. So we know that our torque has to be 1.2. We're looking for what force we have to put on it, and the distance is 0.22 meters. That distance came from my radius, the 0.22. So I stick that in there and I take 1.2 divided by 0.22, and you get 5.5. 5.5 newtons. So, to summarize, we talked about moment of inertia. Moment of inertia depends on two factors. Factor one, where is the weight located? How much weight do we have? That's all it depends on. Where's the weight? How much is it? And from those two things and what shape you've got, and you look on page 206, you can calculate the moment of inertia for any rotating object. That's simple. Newton's second law for rotation. It's just like Newton's second law for linear, except it's for rotational. F equals ma. Instead of force, we have torque. Instead of mass, we have moment of inertia. Instead of linear acceleration, we have angular acceleration. Because remember, we have moment of inertia because there's how much and where. And then I also utilize the fact that acceleration is change in velocity over change in time.